Now we will continue our discussion of weak acids and bases to include full calculations, as we did for strong acids and bases. We'll be using the techniques learned last chapter to solve these problems in a nearly identical manner. In this video, you will learn how to calculate the pH of a weak acid and weak base solution using the weak acid and base approximation. We'll use the 5% rule to discuss the validity of the approximation and learn to calculate the pH of a weak acid or base when that approximation isn't valid. Let's first look at the general plan that can be used for all the weak acid and base problems. We'll want to write out a chemical equation and use it to make an ice chart. I note that you'll want to be sure to recognize if it's an acid or a base equation right away to prevent some errors that can occur later. From here, we'll fill in all the information that we know. Notice that I say to make a note of all leftover information. Although some problems will have unneeded information in them, usually if you are given information such as pH, there is a reason that you'll need it. So if you get stuck, it's good to have a mental note of what is given but not yet used to work from. From here, we'll solve for what we need, typically either using the Ka or Kb and their equation. Finally, the finishing touches. Check that any assumptions used are valid and be sure that units and sig figs are correct. Now let's look at a calculation. We'll do one using formic acid, which was originally derived from ants. We'll start with our basic system of writing out our equation. From here, we'll write out our initial quantities as given in the problem. We've used all the information given, but it's worth remembering that we know what the chemical species we are dealing with is, which means we also know its Ka. We can always look up the Ka of a known species. Now let's keep going. We don't know how much dissociates, and so we'll need a variable as a placeholder for our change row. We can then fill in our final values using this variable. Now we can fill into the Ka equation since we know the Ka, and do the algebra to solve for x. But notice this is a quadratic, and the algebra can get pretty hairy pretty fast. However, because of the weak acid approximation, we can look at the Ka and the concentration. We compare their order of magnitudes, and we see that the concentration is about 1,000 times greater than the Ka. We'd be assuming that the x is very small in comparison to the 0.1, making the equation look like this. From here, we can rearrange our now much simpler equation to get x. Now, since this is the value of H+, we can fill into the negative log of H to solve for pH. But first, we need to make sure that our assumption is valid, or else we would need to go back and solve the quadratic. There are a couple of different ways of thinking about the assumption check. From a conceptual standpoint, what you are really checking is that the percent ionization is less than 5%, to be sure that the idea that we based our approximation on is valid. Or in other words, that very little of the HA dissociates. There is also a more purely mathematical way of looking at it if you prefer those methods. We decided that the x was very small in comparison to the 0.1. So we need to make sure that this is really true. Either way will yield identical mathematics and therefore identical results. In both cases, you are putting x, or the concentration of A-, over top of the initial acid concentration, giving us a result of 4.2%. And showing that our assumption was in fact correct because it is less than 5%. If it were over 5%, we need to go back to the Ka equation and solve it without using the assumption, using the quadratic equation. We can now continue by taking the negative log of x, in addition to being the concentration of A-, it's also the H+ concentration, so this is how we would go about solving for pH. This gives us a pH of 2.37. Let's do the same thing with ammonia now. Ammonia, or NH3, is a weak base. Since we know what species we are dealing with, we should also note that we know the Kb because we can look it up. From here, we fill in the information we know, our initial values. We use x as our variable and find our equilibrium equations. We can fill this into the equation for Kb. If we make the assumption, we get an x value of 3 times 10 to the negative 4th. But we always need to do the assumption check. In this case, putting x over top of 0.005. This gives us a value of 6%, which is higher than 5%, which means that the assumption is not valid and we must go back and solve the quadratic. We'll go back to the original Kb equation and rearrange to put into the quadratic formula, and then solve for x. Since it's a quadratic, you'll end up with 2 answers. Simply pick the one that makes the most physical sense, aka is positive and lower than the initial value of the acid. From here, we'll have our concentration of OH- and can solve for POH, which then allows us to solve for pH. We have now done a few of the simplest sorts of weak acids and base calculations. We'll work on some other variations in class where you are given different sorts of information, but the basic process outlined on the flowchart will still be used.